So I've kind of mentioned inelastic collisions indirectly in one of the last videos I posted, where you had the person kicking the soccer ball and the soccer ball sort of magically stuck to their foot. This is a type of inelastic collision, sometimes referred to as a perfectly inelastic collision. So that's a collision where the two objects, either one of them's at rest and one of them's moving, or they both have some initial speed, but they stick together and then move as kind of one sort of unified system with one velocity afterwards. There are other types of inelastic collisions, because that word inelastic simply means that the kinetic energy of the system is not conserved. So you could have a loss in kinetic energy. You could also have an introduction of new internal kinetic energy to the system. So you'd have a situation where the kinetic energy afterwards is actually greater. And so what I wanted to do is take a look at a situation like that, because these problems tend to be a little bit more difficult. So let's look at this setup. So we have two carts approaching each other. So one has a mass of 0.35 kilograms, and it's traveling to the right at 2 meters per second. And we have another cart. It's a little bit more massive. It's about half a kilogram, and it's traveling a little more slowly at about minus a half a meter per second. So these two carts are approaching each other, and this cart has a spring attached to the front of it. And you can kind of see here that this spring is coiled. So what's going to happen is when these two carts smack into each other, the spring is going to be sort of discharged, and the energy that's tied up in the spring right now is going to be converted into kinetic energy that's going to become part of the system. So we can kind of see intuitively, if we assume that there's no or minimal friction on this surface, that the kinetic energy after the collision is going to be greater than the kinetic energy before the collision, because we have all this energy that's tied up in the spring is going to be unbound and released down here. So after the collision, we know that this first cart, this cart here, travels backward. It recoils at minus 4 meters per second, but we don't know what the final velocity of the other cart is. And we also maybe want to know how much energy was released by the spring, how much energy was introduced to the system. So let's kind of look at how we'd approach both of those questions. You always want to start, even in an inelastic collision type situation, you always want to start with conservation of momentum. Okay, so m1 v1 plus m2 v2 is going to equal m1 v1 prime plus m2 v2 prime. And notice here we know almost all of these quantities. Okay, we know the initial masses and the initial velocities. The masses stay the same, but the velocities change, and there's only one of those velocities that's unknown in this case. So we can kind of rearrange. We want to probably get v2 on one side of the equation, and then we want to get everything else on the other side. So we could write m2 v2 equals m1 v1, and this is m2 v2 prime, equals m1 v1 plus m2 v2 minus m1 v1 prime. Okay, and then we can just divide through by m2 to solve for v2. So we can say v2 prime is equals m1 v1 plus m2 v2 minus m1 v1 prime all over m2. So we can go ahead and plug those numbers in on our calculator. And remember, the direction of these velocities matters. So if you're calling the right-hand direction positive, then the left-hand direction has to be negative, and you have to kind of reflect that in your calculations. So we'll do m1 times v1, so that's 0.35 times 2, okay, plus m2, so that's 0.5 times minus 0.5. Okay, and then we have minus m1 v1 prime, so that's minus, again, 0.35 times minus 4, because we're recoiling, we're going backwards. Okay, So then we're going to divide by M2. Now M2 is 0.5, and so we get that V2 prime is 3.7 meters per second. Okay, so we can kind of fill that in here too if we want. So that might kind of raise the question then, how much kinetic energy was tied up in this spring? And the way that we would do that is just calculate the initial and final kinetic energy of the system and then see what the difference is. So the initial kinetic energy of the system is just going to be 1/2, and we'll have m1v1 squared plus m2v2 squared. And then the final kinetic energy is going to be 1/2 m1 v1 prime squared plus m2 v2 prime squared. And so if we just subtract the initial kinetic energy from this final kinetic energy, we'll get the change in kinetic energy in the system, which is going to be equal to the amount of energy that was released by this spring. So all we have to do, now remember, because we're squaring all of these velocities, when we're accounting for kinetic energy, it doesn't matter as much if we leave the negative sign in or not, because we're squaring everything, so that negative sign is going to be removed kind of one way or the other. So we'll do, for the first one, we'll do 0.35 times 4 plus 0.5 times 0.25, and then we'll multiply that whole thing by 0.5. So we're starting with a really small amount of kinetic energy. We're starting with only 0.7625 joules of kinetic energy. So very little energy in the system initially. And then at the end, we're going to have 0.35 times 16 plus 0.5 times 3.7 squared. Then we're going to multiply that by 0.5. So we wind up with about 6.2225 joules of kinetic energy. So the change in kinetic energy, which is equal to the kinetic energy that's tied up in the spring. Okay. We won't represent that with a delta, we'll just say US. That's going to be, we'll just take the difference, so we'll subtract that 0.7625, and so we get about 5.46. Okay, so 5.46 joules of kinetic energy were in that spring. Now, something you might see maybe on the AP exam, if they put a problem like this on there, maybe they'll even tell you how much the spring was compressed initially, and they'll ask you to find the spring constant, and you could do that. In this case, we can't do that because we don't know how far the spring is compressed, but just kind of another layer of other concepts that they could kind of bring in. So hopefully this is helpful. I'm going to post another video going over elastic and inelastic collisions in 2 dimensions after this, and I'm going to schedule a new assignment on that to post tomorrow morning.